Welcome back to another video in the Descriptive Statistics series. Statistics is the science of collecting, analyzing, interpreting, and using data to make decisions and solve problems. You could then explain the main components such as data collection, data analysis, data interpretation, and decision-making. It also can refer to numerical summaries of data such as averages, medians, percentiles, which we will talk about in this lecture. For example, we will repeatedly use the terms sample statistic or test statistic to refer to these numerical measurements that we obtain from data. In terms of applications, statistics can be used to conduct research, evaluate outcomes, develop critical thinking, and make informed decisions. Statistics can be used to inquire almost any field of study to investigate why things happen, when they occur, and whether its reoccurrence is predictable. For example, we can forecast the weather, measure effectiveness of a treatment in a medical setting, estimate the chances of genetic inheritance, predicting the election winner in politics, or find the likelihood of an accident as an insurance provider. Companies and agencies use statistics to make data-driven decisions, enhance quality, and stay competitive. By analyzing data, they gain insights into customer preferences, improve product reliability, and reduce production costs. Statistics also allow companies to manage risks, forecast demand, and optimize resources in areas like inventory and scheduling. For example, statistical quality control techniques help maintain consistency and reduce defects, while market analysis guides product development and marketing strategies. Overall, statistics enable companies to make objective, evidence-based decisions that drive efficiency, customer satisfaction, and growth. Statistics helps us to design study to answer the question at hand, collect trustworthy data, analyze data appropriately, draw reliable conclusions, and make informed decisions. Examples of improper uses of statistics include bias samples. During the war, American military analysts were studying the bullet holes on planes that returned from combat missions to determine where to reinforce armor. They noticed that the returning planes were most damaged on the wings, tail, and fuselage. The initial suggestion was to add armor to these areas, assuming these were the spots most likely to be hit. However, Wald pointed out a crucial insight. They were only looking at planes that had returned from missions, meaning these planes had survived despite damage in those areas. The areas without bullet holes on the surviving planes, like the engines and cockpit, were likely where planes had been hit and not returned. Wald recommended reinforcing these less damaged areas, reasoning that planes hit in those spots were more likely to be lost in combat. Looking at the unprovoked shark attack map, I can claim that it seems most unprovoked shark attacks happen in the coastal areas, so it is safer for us to swim in the middle of the ocean to avoid such attacks. No, the claim is not correct because it misunderstands the context of the data. While it's true that most unprovoked shark attacks happen in coastal areas, this is largely because that's where people are swimming. The higher frequency of shark attacks near the coast doesn't mean sharks are less likely to be in open water. Rather, it reflects human behavior. People are far more likely to swim close to shore than in the middle of the ocean. Sharks also inhabit open waters, but attacks are less common there simply because there are fewer people swimming in those areas. Thus, this conclusion represents a sampling bias by assuming that the location of attacks reflects shark presence rather than the high concentration of swimmers along the coast. Loaded questions are worded to lead respondents toward a particular answer. For instance, asking, "How satisfied are you with our excellent service?" implies that the service is good, which can bias responses. Such questions manipulate data collection, making the results unreliable. Results can be presented in a way that exaggerates findings or omits important context. For example, displaying data with manipulated axes and graphs to amplify small differences can mislead the audience into believing a trend is stronger than it actually is. Overgeneralization occurs when results from a specific sample or context are incorrectly applied to broader populations. For instance, if a product test is conducted on a small, non-diverse group, it may not apply to the entire customer base, leading to faulty conclusions. False causality arises when a correlation between two variables is misinterpreted as causation. For example, A company may notice that ice cream sales increase with temperature and mistakenly conclude that higher ice cream sales cause warmer weather. Statistics cannot prove causation without controlled experiments or additional supporting evidence. The case in point here is that the main cause of divorce is marriage because 100% of people getting divorced are already married. This claim is misleading because it mistakes correlation for causation. While it is true that 100% of divorces occur between people who are married, since only married couples can divorce, this does not mean that marriage causes divorce. The null hypothesis is typically a statement of no effect or no difference, and statistical testing can only reject or fail to reject it. Misinterpretation occurs when researchers claim to prove the null hypothesis. However, failure to reject it doesn't confirm it. It simply means the evidence wasn't strong enough to support an alternative hypothesis. We have a deeper dive on this improper use of statistics when covering hypothesis testing lecture. And finally, incorrect choice of analysis or assumption violation. Statistical tests have underlying assumptions, like normal distribution, independence of observations, etc. Using a test without verifying these assumptions, such as applying a parametric test to non-normally distributed data, can lead to inaccurate results. Choosing an incorrect test or ignoring assumptions can invalidate the analysis. There are two major branches of statistics: descriptive statistics and inferential statistics. We will start by going over descriptive statistics. Descriptive statistics describe or summarize data more clearly, using measures of central tendency, measures of dispersion, and visualizations. Measures of central tendency, such as the mean, median, and mode, give us an idea of where most data points lie. As seen in the bottom left figure, the central tendency can help us to locate the peak of a distribution or where our observations have the highest frequency. But it is also important that not always all central tendency measurements point to the same conclusions. The bottom left figure is illustrating 3 different populations, and it's only for the one in the middle where mean, median, and mode are all reporting the same value. Whereas, in the left and right figures, the mean, median, and mode are reporting different values as the peak. We will discuss the reason behind this later in this lecture. Nonetheless, it is important to remember that the selection of central tendency statistics might result in different conclusions, and it is up to you as the statistician to select the right one. Measures of dispersion such as range, variance, and standard deviation tell us how varied the data is. The figure on the bottom right demonstrates how 3 different populations with the same peak or same central tendency can have completely different measures of dispersion. This means that knowing about central tendency of a population is not enough, and to have a good understanding of how a population behave, we need to understand its central tendency and dispersion. Visualizations, charts, graphs, and tables help us see patterns and trends. Inferential statistics is a branch of statistics that allows us to make conclusions or predictions about a larger population based on a smaller sample of data. The population is the entire group you want to study, for example, all the students in a university, whereas a sample is a smaller group taken from that population, for example, 100 students from the whole university. Since it's often impractical to study an entire population, we use samples to gather data. You might ask, given that descriptive statistics helps us to summarize data, why do we need to use inferential statistics? Inferential statistics helps us make inferences about the population without needing to collect data from the whole population. This is especially useful when populations are large or when it's costly or time-consuming to collect data from everyone. Key concepts of inferential statistics include sampling, hypothesis testing, and confidence intervals. We will be covering these key concepts through the semester. Inferential statistics are widely used in engineering, business, healthcare, and social sciences to analyze data, guide decision-making, and predict future trends based on current data. In summary, inferential statistics provides powerful tools for drawing conclusions about a population from a sample, allowing engineers and researchers to make informed decisions without needing exhaustive data collection. Thank you for watching this video.